Read this problem. So we have been given a vessel, and this vessel contains 6 gram oxygen and 9 gram of methane. Both are gaseous, and the volume of vessel is 15 liter, and temperature is 273 plus 0, that is 273 Kelvin. And we have to calculate what is the pressure due to CH4 and pressure due to oxygen, that is partial pressure of each gas. And we have to also calculate what is the total pressure. Now how we'll proceed for this problem? We will apply ideal gas equation for methane to get the partial pressure of methane. Similarly, we can apply ideal gas equation for oxygen to get the partial pressure of oxygen. That is, we have to apply separately. So plan will be apply ideal gas equation separately for oxygen and methane. So let us say first for methane. So we have been given mass of methane is 9 gram. So we can calculate mole from here. So moles of methane, that is weight by molecular weight, and molecular weight is 16, and the volume is 15 liters. So even for methane, we'll assume this methane molecule is free to move everywhere in this vessel. So volume occupied by methane is also 15 liter. So volume is 15 liter, and temperature is 273 Kelvin. So let us apply for methane. PV is equals to nRT. So I will have P is equals to nRT by V. So if I need for methane, I have to take the moles of methane into R into T divided by V. So N-methane is 9 by 16. Let us say this is mole. R is 0.082 liter into atmospheric pressure divided by mole into Kelvin, and temperature is 273 Kelvin, and this divided by volume is 15 liter. So you see liter goes, atmospheric pressure also goes, so we have to see atmospheric. Okay, atmospheric pressure does not cancel, so we have mole that cancels, Kelvin cancels, so we will have pressure is equals to 9 into this divided by 16 into 15 atmospheric pressure. So calculate this value. So this value is 0.839 atmospheric pressure. Similarly, we can do for oxygen. Now oxygen is 6 gram. So let us do for oxygen. So moles of oxygen, that is 6 divided by molecular weight 32, and that is basically 3 by 16 mole. volume remains same, that is 15 liter, and temperature also remains same, that is 273 Kelvin. Now I can apply PV is equals to nRT. So we will have from here P is equals to nRT divided by V. So let us say PO2 is equals to number of moles of oxygen into R into T divided by volume. So if I plug this value, number of moles of oxygen is 3 by 16 mole, R is 0.082 liter into atmospheric pressure, mole into Kelvin, and temperature is 273 Kelvin, and volume we have 15 liter. So liter goes, mole goes, Kelvin also cancels, so we will have 3 into 0.082 into 273, 16 into 15, and the unit will be atmospheric pressure, so we will have this in atmospheric pressure. So let us calculate this value. 3 into 0.082, 273, and this divided by 16 into 15. So this is 0.279. So this is 0.279 atmospheric pressure. So this is the pressure due to oxygen. So we know pressure due to oxygen. We also know pressure due to methane. This is the pressure due to methane. Now we can apply it to calculate total pressure. The Dalton's law says total pressure is sum of the partial pressure. That is partial pressure of CH4 plus partial pressure of O2. So this I am applying using Dalton's law. And what this law says, total pressure is basically total pressure is equals to sum of the partial pressure. So if I apply this value, P total is equals to PCH4, and this is 0.839, 0.839, and P oxygen is 0.279. Now if we add these two values, so this is around 1.118, or I can write 1.12. So this is 1.12 atmospheric pressure. So you see what we have done in this problem. This is related to partial pressure. So first we have calculated partial pressure, and this using for partial pressure we use the formula P is equals to nRT by V. If I have ith gas, so I can write Pi is equals to NIRT divided by V. And if I need total pressure, so total pressure will be nothing much sum of the partial pressure, that is summation of partial pressure.